All right. Welcome, everybody, and thanks for joining Tim and me at building a self-driving RC car. Who would have thought when you were planning to go to Devoxx that you were sitting in a room with, I don't know, a few hundred people, looking at two grown-up men and their toy car? Well, here we are, so we might as well make the best of it. Before we introduce ourselves, we're going to start with a demo. So we're going to spin things completely around. Start with the accelerating demo right away. And I must say that this is the scariest demo I've ever done. Because typically when I demo stuff, my hands are on the keyboard and I can control what's going on. And in this case, I can't touch the keyboard because the car should drive itself, right? So we have the car up front here. What you're seeing on screen is our web interface where we can control it. We'll talk all about this later. And the objective now is that the car I will start the car. It should drive itself, stay between the white lines, and then stop when it's not seeing any lines anymore.
So if everyone will cross their fingers now, right? See if it works.
If you're up front, I would advise you to lift up your legs. Because we have, we have an idea what's going to happen, but unexpected things happen all the time. So let's see, we're connected. Here we go. we were smelling it a little because we've practiced with floors that are have an even color, like the black carpet up there, and the floor here is spotty. So it was detecting all these white spots as little white things that might be lines. So it was a bit troubling, but luckily we could tweak the thresholds of the line detection a bit, but a lot more about that later. So let's start with the beginning. My name is Bert Jan Schrijver. I'm a software craftsman at JPoint in the Netherlands. And at JPoint, we typically build stuff for various clients throughout the Netherlands using Java, web stuff, and other stuff. I also work at OpenValue, which is a small Java startup in the Netherlands. And I run the NLJUG, which is the Dutch Java user group. I know we're not in the Netherlands, but are there any NLJUG members in here? All right, way to go. And I'm here together with Tim.
Yes, my name is Tim van Eijndhoven. I also work at JPoint, and I'm currently hired by Malmberg, an educational publisher, where we do other cool stuff.
So is this what we do all day, building self-driving cars?
No, I don't, do you?
Well, I've been for the past days, but that was kind of more conference-driven delivery. So how did this all start? As I said, we work at JPoint, and at JPoint we typically do fairly serious stuff for clients. So Java development, web development, bit of continuous delivery, DevOps. You could even call it enterprise, but just stuff for clients in the Netherlands. And every now and then we want to do something completely different. So we gather around with the whole team and we spend a day working on, projects of our liking. So one of our colleagues once transformed his Roomba vacuum into a controllable device that could play the Dead March. That was a day well spent. We've done some other miscellaneous projects, but one of the projects we worked on is this project. And I think actually the idea came from our bosses, who said, well, let's do something cool and challenge ourselves a bit and dive into a field that we don't have any experience with and see if we can make a car to drive itself. So it started with this. We formed 4 teams, and we all got a basic RC car kit and some hardware, and that was it. We had a laptop and the internet to try to find out how to make it work. So this is the challenge we set. 4 teams. Every team gets an RC car kit, just a basic thing you can buy in the stores or pick up online. I think it will set you back around 150 or maybe 200 euros. We got a fixed budget for sensors and other hardware on the car of 150 euros. And then there's 3 races. The first race is just a straight line. So we start in a start zone. There's a starting light. When the light goes off, the car needs to drive. Then it needs to follow the 2 lines for 50 meters. And then in the end, there's a stopping zone of 1 meter wide where the car needs to stop automatically. So this race we've already done. Then the next race, which is scheduled for March, is there we actually corners we need to navigate to the track. And then the third race, we'll have multiple cars on the track that need to avoid each other. Or, I don't know, if you're stronger than the other car, then avoiding isn't necessarily what you need to do. But you need to navigate yourself with multiple cars on the racetrack with corners. So this is what we have. It's a fairly basic RC car kit. Let me grab it real quick. It has wheels, like most cars. 4 even. It has a servo to control the wheels. It has an engine, a speed control that will make the car drive, and then a frame and a battery to power the whole thing. So then we needed something to control it. And every hobby project gets cooler if you throw in a couple of Raspberry Pis, right? So we had a Raspberry Pi 3 laying around, which is actually pretty good for a project like this because it's small, it's light, it doesn't consume too much energy, and it's fairly powerful. You have no trouble running a JVM on there. So it needs power. So what we did is take a small converter that will draw power from the car battery, which is 11 volts, and then convert it to a 5-volt USB connection. So we can power the Pi from the car battery. Then we need something to run it on. We like Java, so we run on the Java platform. We chose to run it on Vertex, which we were both familiar with from our work at Malmberg. And Vertex is a toolkit for building reactive stuff for very general purpose, non-opinionated. It is event-driven and it's non-blocking. And we mainly chose it because it's very lightweight, both in terms of size and in terms of memory and resource consumption. It is polyglot, so we had the idea of maybe using different languages in the beginning. We ended up by using only Java. And the main thing for us is Vertex has a distributed event bus. So with Vertex, you program what you could call services, and these services are all connected together through the Vertex event bus, so you can send messages to each other. And this event bus also works over the network and even all the way to the browser. So by using Vertex, just with a few lines of code, we can have code running on the Raspberry Pi on the car. We can have code running on our laptop, and we have code running in the browser, and we can easily send messages through all those stations. And the distributed nature of Vertex really helps us in terms of fast development. So we can, when we're developing, we can run only the core controller of the car on the Pi, and run all the rest on our laptop. And then whenever we want to move to, well, let's call it production or more definitive phase, we can move services from the laptop to the car by just deploying them there. They all stay connected via the event bus. So if you're interested in Vertex, I had a lot of fun working with Vertex. I did a talk on it once. It's on YouTube. You can go ahead and watch it there. So then we have the Pi running there, and we need to connect it to the car. So there's two things that a car needs to do. It needs to drive, so there's an engine, and it needs to steer. So there's a steering servo. So these are typically controlled by a wireless receiver. So you have a receiver in the car, you have a remote control with 2 channels, forward, backward, left, right, and then this receiver sends signals to the servo, which is like a small motor that can go either both ways. So it's connected to the wheels, so the wheels can turn, and to the speed controller, and the speed controller feeds power into the engine, which is either no power, then it's still, or maximum power one way, it's going maximum speed forward, maximum power the other way, or anything in between. So we hooked those up to the GPIO ports of the Raspberry Pi. GPIO stands for General Purpose I/O, which stands for General Purpose Input-Output. And the GPIO pins are pins that you can connect all sorts of stuff to your Raspberry Pi. So there's 2 pins with a current on there, either 5 volts or 3.3 volts. There's a few pins with ground, and there's a lot of data pins. So typically you connect the device to the 5 volt or 3 volt, to the ground, and to a data pin. So then we have them connected, and then we need to make the Raspberry Pi talk to the steering servo and to the speed controller. And this is typically done by a signal called PWM. PWM is pulse width modulation. Pulse width modulation sends repeating pulses, and it varies the width. So it uses this to basically set numbers over a wire. And we use a utility called Servo Blaster for this. Servo Blaster is a small Linux utility. It runs as a daemon on Linux and creates a device, Dev Servo Blaster, where you can send commands to. And it can control up to 8 servos. In our terms, we've hooked up, in our part, we've hooked up 3 things. One is the steering servo, one is the speed controller, which is also controlled by PWM, and one is a LED, which turns out to also turn on when we send the PWM signal to it. So that was nice and comfy for us. So let's say we want to hook up something to servo number 0, then we need to be a GPIO port 4. So if we go back to the diagram, we would need 5 volt because the servo is operating on 5 volt. We need a ground connection and data connection 4. So this is where the servo is hooked up to. And if you have this, then you can send commands. You can just say echo 0 is 150 to Dev Servo Blaster, and then Servo Blaster will send the PWM signal. So that's all you need to basically control the car. Servo Blaster is open source, is up on GitHub for you to grab. And this is, actually, I think this is a very powerful piece of software because you can just use this to control whatever servos you have with your Raspberry Pi. You can create a tank, you can create a webcam, you can create an automated door lock with a servo to, I don't know, pull the door. So for me, it was a nice piece of software to look at. And so then our first prototype was, we had the Raspberry Pi, Servo Blaster one there. We would have a Wi-Fi connection to the Pi with a laptop, log in over SSH, and then we were just typing echo 0 is 250 to dev Servo Blaster. And then it would start driving, and it wouldn't stop anymore. So then we would type echo something quick that would make it go left, and echo something else, go to the right, and echo something else, and it would stop. And we really quickly noticed that this approach didn't really scale. Because we ended up running most of the time, running after the car to go fetch it. And we have a fairly large hall next to our office, and this is where we really need to exercise a little. So we figured out that we need to work on some safety measures first. So what we're doing is the control server that's running on the laptop is sending a heartbeat signal every 100 milliseconds to the Pi. And if the Pi doesn't receive, I don't know, 2 or 3 of these signals, then we'll shut down just as a safety measure when the Wi-Fi connection is a bit spotty, or maybe the Wi-Fi connection drops, or the laptop shuts down. So safety, even in such a small situation, was fairly important for us. And then we need to see. So we grabbed the Raspberry Pi camera. You can pick them up for somewhat 30 euros, hook them up to the board, and then you can get a camera feed. And for this we used our Pi Cam web interface, which is a Linux utility you can run on your Pi. It will connect to dev video and then send out a video feed over HTTP. So you can do MJPEG streaming from the device. And it has a web interface to configure video settings. So you can set stuff like white balance, the metering mode, brightness, saturation. So this helps in terms of tweaking the video image, because it turns out that since we only rely on video, having a clear video image is really important, because we're very susceptible to light differences. We even noticed here that the spots in the floor were troubling for us, so we needed to tweak right before we started. So then I would say we're ready to drive, right? We have a video image and we can control it with a keyboard, and we're ready to get going. But eventually we want to make it drive ourselves. So this is how our interface looks like. We have the camera image. We have some controls here. You can just put left, right, up, down. And we have the events going over the Vertex event bus below. And then we have some other images here that seem to do some stuff with lines. And I believe that Tim is going to share all about this.
Yes, so we could drive the car now by hand, and the whole challenge was to let it drive by itself. So we needed to actually let it think for itself on how to drive. So we decided, because we had a limited budget, of course, to go with the purely the optics, right? The camera, in order to detect where the road was and how the car should navigate. And in order to do that, we needed to interpret the image, right? So as a human, you look at an image and you see, oh, that's a white line, so that's the boundary, and that's the other boundary, and that means that the road's in between. Well, we needed to let the car do that as well. So we needed some sort of image processing. And we knew about OpenCV, and it's to our knowledge, it's the most widely used open computer vision library. It's written in C++. It has Java interfaces, which was important for us as well. And there are many resources available online on using OpenCV for all different sorts of computer vision, but also many on the subject of lane detection. So basically what we do in the image processing pipeline is 2 major steps. So the first one is actually to find the edges in an image. And we do that using a canny edge detection, which is an algorithm which dates back to, I think, the 70s, so it's way old, but it's still about the most widely used algorithm to detect edges in an image. And then we needed to convert those edges into lines, so to interpret where are lines in our image. And for that we use the hue line transform, and actually we use the probabilistic version of it. And the only reason why is because we read somewhere that it was faster. So we use those 2 things to detect the lines. And then as you can see in the top right image, is that there's in the top right corner there's a horizontal line, right? So it detects all lines in an image. So not only the ones that we want, but it detects all. So then we filter them, and we can do that because we know that the image will look at the road in a perspective. So we know that the road is doing this, right? It will join to the top. So we can actually filter the lines based on a predicted angle with some sort of margin. And then we can determine where the lane center is by doing some geometry. And we can determine what's the angle of the car and what should we do. So let's go into some of the code. Different combo.
Sorry, my machine.
It's
my
a different laptop. Sorry. So basically, what we have is a class that does the lane detection in an image, and because a video feed is nothing more than a stream of images. So, in order to detect the lane, the first thing we do is we determine a region of interest, because the image will contain a horizon, and above the horizon is, well, at this point, it's not interesting for us. All we need to know is to see what's on the ground, right? We need to find a road on the ground. So we can drop the top half of the image, which is well, half the image processing, which means speed. So we take the bottom half of the image to process, and then we have what we call a line extractor. And this class, well, it basically takes two arguments. One is the canny edge detector, and the other is the hue lines detector, which runs on top of that. It takes a configuration to set some parameters. And this canny edge detector that we have basically is a wrapper around a OpenCV call. It's nothing more than that. So this line that I'm currently highlighting is the call to the OpenCV library to do a canny processing on an image. And this produces that black and white image that we showed earlier.
So this is running on a native C code.
Yep.
In OpenCV, yeah.
It's native C code.
It took us, I don't know, about a day to compile on Raspberry Pi, I believe.
Yeah, that has challenges on its own, yeah. So, and then we have the line detector, which contains a bit more code, because actually we go from the domain of OpenCV, which is like a matrix and vectors, into the objects that we want to use in our Java code, which is a line. But still, the whole processing is, again, just a one-line call to OpenCV. So in order to do the processing on the image that we do to detect lines, it's only two calls to OpenCV. So that's, I think it's pretty easy to do, actually.
As long as you know which calls to make.
Right, yeah, that takes some finding out.
That's what all the code you write, I guess.
Yep.
It's not the typing that's the bottleneck, typically.
Exactly. It's the person behind it, right? So, and then we have the lane detector. So this takes the input, the lines that we've detected, and actually it uses two classes like the lane left boundary and the lane right boundary, which filter those lines based on an angle. So the expected angle that we do for the left line and the right line, and a tolerance. So basically, that gives us two sets or two lines that define the whole lane that we drive in. Oh wait, I'm not finished yet. So now that we have this, we can actually filter that stuff and do some calculations on it. So now that we have the lane, we can actually calculate the important stuff for us to navigate. So which is basically the angle, which is what we use at the moment for navigating. So we see that the car is at an angle on the road, and then we determine what angle should we steer in order to go straight through. So basically, that's our whole image processing pipeline. Now going back to my presentation. We actually thought we needed an architecture, right?
Who doesn't?
Every project needs an architecture. So this is our architecture diagram. And do these names make any sense to anyone?
Yes. Shout it. Dukes of
Dukes of
Hazzard,
Hazzard, right. So that was our team name, the Dukes of Hazzard. So we thought it would be a great idea to call our services to the characters in the show. I can tell you now that's not a good design choice, because every time we have to look into what's doing what again.
I need to open the README every time to see which service I need to start up. So, yeah,
right.
Great idea. Not really.
So the code that I showed you is in Daisy, actually. So Daisy takes the input from the camera and does the image processing on that. And we have a debugging service, Roscoe, which actually ties into Daisy and then provides those images to our UI. This is not necessary for driving, but it's necessary for us to see what's happening. Daisy does this analysis and then calculates like the angle and the distance that we have on the lane, and then it's communicated to Luke, because Luke always was the smart one in the series, right? So he's the one that actually gets told this is how the road looks, and he decides what to do with navigation, which he then instructs the steering speed to Bo, who always drove the general lead. So that's the service that gets the input from Luke that says, well, we need to steer like a certain amount of degrees to the right, to the left, and we need to accelerate or decelerate. And then it uses a library that in Java, which actually echoes the commands to Servo Blaster to do the steering inputs and the engine inputs. On the other end, we have Boss Hog, which is our UI. So that's the whole puppet master when we do this ourselves. Whenever we have the control to start or stop the autopilot from Luke, right? And the other end, we have the manual inputs which get sent directly to Bo in order to steer the car. And it sends the heartbeat to Flash. Flash the dog on the series, and he's the one that does the heartbeat control, and that actually lights up the LED to show that it's connected, or dims it when it's disconnected, and whenever it disconnects, it will stop the engine. So that's our architecture, and these two areas that we have. The right area is the stuff that runs on the car, and the stuff on the left what runs on the laptop. So that's basically our architecture for software for a self-driving car.
Thanks for the explanation. It all makes a lot of sense to me now. It's the first time I'm hearing this, so.
It was designed after quite a few beers, I can tell you.
I can't remember.
So now that we have this, right, it must be awesome. I mean, we have to take the software and put it into. Actually, our boss has a Tesla, so maybe we can upload it there, right, to see if it works.
Yes, should work.
What could ever happen?
Yes. So, we built a Tesla, right? This is exactly the same. So this was our expectation. Fully self-driving, automated, autonomous, awesome car. Our reality is more like this. It drives itself when we're lucky. But yeah, there's lots of rooms to improve. I think that's a positive way to look at it. So here are some videos of us building this thing. So this is in my kitchen, and we've built a full-fledged racetrack here. So you see the lines. Here's the starting light, and then here below is the stopping zone. So we're doing an entire race in 2 meters.
Yeah, actually, it has to autonomously look at the starting light as well. So so when the light dims, it should start.
Yeah. So let's see if this works. Here we go. So what it does is just it.
This was a major success for us.
Yes, definitely. Yeah, it looks at the start light, then it starts driving, and then it stops in the stopping zone. So that's right. Let me see if we could get some audio there, because I think we forgot to set this up. Should we send this over HDMI audio or over jack? Yeah, got it. Because there's one video that I really want you to hear the audio in. It's one of the final ones. Okay. So, this is the first one. Then let's move on to the second one. This is a bit longer track. What we're doing here is practicing whether it can drive over a longer distance. So you see it making small steering adjustments, which works fine, but what we're seeing is that when we're driving longer distances, the car tends to swerve a bit, because we're steering based on the angle that the car is making with the road. So it's it's approaching the lines of the road on an angle, then it steers the opposite direction, and we kind of oversteer a bit. So then we need to compensate again, and then it starts swerving a bit. So we did some damping to this, but there's some room to improve here.
It still looks like a drunk driver.
Yeah, definitely, but autonomous drunk driver, right? So that's better.
That's right.
So while we were recording this, there was so our office in a big hall. So typically there are events there and expositions, and there was I think it was like a baby exposition where you could buy all stuff for your baby. And this is where we were driving. So the video you just saw was recorded here, and there's a small pass through here. So our car was so smart and steering so well that it ended up going in there, going through here, navigating swiftly between those two plywood pieces and driving onto the baby show.
It didn't hit anything.
It didn't hit the walls. Now, what I'm thinking is that maybe it saw these as lines, I don't know. But I ended up running into the baby show and all kind of amazed people there by what this little car was doing. It didn't hit anything, so it behaved well, but still. Interesting stuff can happen. So this is a bit more advanced setup where we're driving inside our office, and there's some different lighting conditions there. We've had some small curves in the road, and after a few takes, it also worked all right. It's about to stop at the most important space in the office. The bar, obviously. So as I said, it took us a few takes, and I think it's good that we also show one of the situations where we kind of missed it. So yeah, this happens all the time. We were discussing what caused this, and maybe it's all the reflection of the lines in the mirror here, or maybe some shade or something. It's fairly hard to debug, since then you need to be looking at the output all the time. So building this, we got a lot more respect for Tesla and the likes about how they do it. But still, we were fairly happy with the result. So we had our first race, which was I think last year. We did a day of hacking in the office and practicing and driving in the hall under perfect lighting conditions. And then for some reason, we decided that was a good genius idea to do the race at night. And what happens typically at night, it gets dark. And now we couldn't see the road anymore. So we brought some cars in, some big lights, but it was horrible because there were all kinds of shades on the track, and if we could set the brightness good for one portion of the track, but then it would fill another portion. So of those 4 teams, one car didn't actually drive at all. The other was only manually controlled, and 2 cars actually drove autonomously. So we raced with those 2 cars. The other car actually made it all the way to the end in the track, but it switched lanes halfway. So then we counted the distance that it did in its own track, and our car didn't make it to the end at all, but it drove maybe 2 meters further than the other car. So that's why we won. But I need to say that we actually thought that the other car was better.
The other car was
so this car was created by Gijs, who is actually in the room. Can you stand up, Gijs? So let's give a round of applause for the actually winning car of Gijs. We have a lot more races in front of us, and also a lot more work. But this was a fun thing to do. So, would you drive this car if it was driving in the real world?
No way.
No, me neither.
Way. I don't trust my own programming in this. But that's an actual problem, right? Because now we have all these cars on the road, which actually do self-driving, more or less. So this is a real-world problem, and there are different solutions for it. So let's look at self-driving in the real world. Well, there's a categorization of the autonomousty of a vehicle. At level 0, you have nothing, right? You have to do everything manually. Then at level 1, you have a car that can handle one task at a time, so it can do an emergency stop when a pedestrian crosses, or it has like the adaptive cruise control, like that sort of stuff. And then you have level 2 cars, which can do 2 automated functions, so probably a car that not only can do the adaptive cruise control stuff, but can also keep the car in lane. And then at level 3, you have cars that can actually do dynamic driving tasks, right? So they can switch lanes and do all sort of stuff without human intervention. A human still needs to pay attention to the road. He has to be there to intervene, but the car can do stuff autonomously. So now, I think most cars on the road nowadays are either level 1 or level 2 cars. And then you have the cars like the Teslas, which are actually level 2, level 3 in under certain circumstances. And then you have level 4, and that's where Waymo's at the moment. So a couple of weeks ago, they announced that in Phoenix they will drive driverless cars around, so you can use them as a taxi. And there is no one behind the wheel. So the car can drive itself fully autonomously. There are videos of it on the internet. It's really impressive.
And it's not like there's a guy in the front seat dressed as a car?
No, it's not.
Dressed
really.
as a chair?
Yeah, it's really awkward to see a car coming up to an intersection and then to see the whole front seating empty. And then it just crosses. It's amazing.
For me, it's already strange to see when a car from Great Britain is driving next to me.
Oh, right, yeah,
so far away,
car, yeah. So and then level 5, those are cars that can do it in like any situation.
Are there any level 5 cars around?
No, not that I know of. But that would be a pretty impressive feat. I
mean, there's room for improvement for us.
Right, yeah, right. So that's a niche in the market that we can drop into. Yeah. Perhaps we should aim for that. So this is a picture from Waymo. So how do they do it? I mean, we do it with just one camera. Obviously, that's not enough in real-world situations. So the Waymo car actually is based around a LiDAR system, which is a laser-based radar system. We looked into it for our car, but it's way too expensive. It's like, I think it's $80,000 for one of those units, so that's pretty steep.
Not really a bargain.
No, it's not a bargain.
Compared to the $30 Raspberry Pi camera,
right.
I think we're on the good side.
So I think relatively we're doing a good job there.
Yeah, definitely. Yeah.
So, and it's actually augmented with all other kinds of sensors. So they have visual sensors and they have like radar systems which support that LiDAR system in self-driving. When you look, this is somewhat what a LiDAR vision would look like. So it's pretty detailed, right? It's 3D. And actually, as you can see on the road, it can see the difference between the pavement and the lines. So you can actually use it for that type of detection as well. And it's not as limited as a camera for the conditions, right?
But I would argue that this looks exactly the same as a camera feed with some coloring in there.
Right.
So what's the difference?
Yeah, right. So it's pretty impressive. And actually, they're currently mapping, I think, the whole world with this system.
So is there does a LiDAR work better when there's like foggy weather or bad light conditions, or why shouldn't they just use a camera?
I would imagine that this would work in, for example, foggy conditions, where visibility is limited. But this radar system will just look through it.
Yeah, it's also a 3D model.
Right. Yeah, it's 3D model. Yeah, that's also one of the major advantages. Yeah. So this is what Tesla is doing, and then they basically base their system around the optics, right, like cameras, which makes it way cheaper to create, and it's augmented with stuff like radar. So the 3D aspect is lost in the video in the 2D video aspect, but they have stuff like radar to compensate for that. All in all, it's a way cheaper system, but it's arguably less robust. What can you imagine it looks like? Well, something like this. So it can detect the lines, it can detect the cars around you purely by optics. And this is not a picture from Tesla. It's actually a picture from the website of Coma AI, which is created by Devoxx, which is a famous iPhone.
I think he was one of the first to create an iPhone jailbreak.
Yeah, it's an iPhone jailbreaker, right? Yeah. And actually, I think it was a month ago that he started hacking on his own car to build his own self-driving car, right, on his own. And now he's actually building a company around it. And I mean, this is really impressive. So
how does the system work? I see he has his phone hanging there.
Yeah, which is basically just a camera, and then it ties into the car via the ODB port, and it can hook up to the CAN-bus protocol in the car, which. That's another part. Well, I will come to that. Nevertheless, it's pretty darn impressive.
Yeah.
What they're doing.
The lane assist and the adaptive cruise control to
Yeah, right.
the car,
Yeah, to actually control the car. So
I would say it's fairly cheap. And
yeah, it's relatively cheap. So, well, there are some safety measures and precautions that the companies take. So, for example, the Waymo cars are geographically limited. So they only drive around driverless in the Phoenix area, which is not just a random decision. It's because they have fairly good road conditions and always fairly good weather. So that will create ideal circumstances to start having these cars driving on their own. The systems in those cars are redundant, so they have two computers. If the main computer drops out, then the other takes over and can bring the car to a safe stop. Multiple sensors, which they can help to to check the readouts to see if they have the correct picture. They isolate the control systems from, for example, the Wi-Fi in the car. I mean, it would be pretty nasty if you could screw up the system by browsing the internet.
Maybe put on a random USB stick and then
Right, and then of course, I mean, most of those cars still have the fallback of human intervention, right? Someone at the wheel who can intervene when something is going wrong. But when something goes wrong, I mean, there is a whole ethical dilemma. So this is one of the comics on the Devoxx website, actually, in which the decision is made if AI or human programmers should program the ethical logic in a self-driving car. And the AI says, well, I think the car should be preserved at any time. Well, perhaps humans should program it, because that might not be the best outcome. But, I mean, it illustrates that there is a whole world of ethical dilemmas behind these self-driving cars. So let's go to one of the oldest ethical dilemmas in human history. Cats versus dogs, right? So we have a situation in which a self-driving car is in an unavoidable accident, and it can go straight through, killing 3 dogs. Or it can swerve, killing 3 cats. So a show of hands, who would save the cats? Okay, who would save the dogs?
I'm more of a dog person.
Oh, wow. All dog persons in the room. This is a hostile environment.
You could argue that the dogs would do more damage to the car than the cats.
Oh, yeah, of course. But now let's get a bit more serious, because this is, of course, a funny example. But what if you have a car which is full of people, right? A family driving down the road, and there's a family crossing the road, and there's an unavoidable accident. And the one choice is to drive over the pedestrians, killing the walking family. Or the car can decide to actually take evasive action, and thereby sacrificing the people inside. Now, who would choose the scenario in which the car sacrifices itself?
Your family is in the car.
Yeah, it's your family, right?
Yeah.
Okay, well, that's still quite a few. But those are the kinds of decisions that come with driving these things in the real world. So, let me ask you, who would want a self-driving car?
So I can check my Twitter on my way to work. Right?
And now, who would want a self-driving car that takes the decision to sacrifice the people inside, your family? These are way less hands than before, right? So this is a real issue. I mean, it's bad publicity, but there has to be legislation in order to give the creators a framework in which to build these ethical decisions on. Now, these scenarios are actually provided by, or I created them in the Moral Machine, which is from researchers that do research into what humans would do in these kinds of situations in order to, well, solve the issue of what should be the ethical or moral choices that self-driving cars would have to make. So go to the website and you can actually answer all these different types of questions, and it will show you where you stack up to the rest with regards to the decisions that you take. And the German government actually issued some rules or some laws actually a couple of weeks ago, of which 2 actually, well, hit this point of ethics. And one is that in these situations of such a hazardous situation, then the preservation of human life should take precedence over all else. So over property damage or animal life, the human life should take precedence. And the other one is that whenever there's a choice to make on who to kill, so to say.
It's called who to preserve.
Right. That's a better option, right? Yeah. So if you have to make the choice on who to preserve, you cannot base this choice based on personal features like age, like gender, or physical, mental constitution, or social status. So this is basically like some sort of protection against all sorts of bias.
If you're reading this, it makes sense, but I could make an argument against it. If you need to choose between hitting someone on the right side of the road or on the left side of the road, there's maybe an elder person who maybe has a couple of years to live and on one side of the road, and there's a young child on the other side of the road. I don't know. Then I don't know if you shouldn't make any distinction based on personal features.
Yeah, so. Well, that's true, but actually it's legislation, so you can't. Can you imagine being the programmer, having to program the lines, right? So based on if age is more than... Well,
I wouldn't even know what I would do if I was in the situation behind the wheel myself, so...
Damn.
Yeah.
So it's really hard.
So on a more light note, back to our pet project. Are we done? Is this perfect? No, I wouldn't say so. No, there's lots and lots of stuff to do. So first, we're now steering only on the angle that the car is making with the lines of the road. Steering on your position on the road would probably be a lot better. We are not currently able to detect and navigate through curved lanes. We would like to make the line detection algorithm a lot better. I think we could really help us. We could automatically calibrate the video parameters, brightness, contrast, lighting, and the OpenValue parameters, the thresholds for the candy detection, for the line detection. We need observability in our car. So currently we're just letting it run and then seeing if it crashes or not, and then thinking, well, this was good and it wasn't, and then change some code and try it again. So we need to be able to tap in what decisions did the car make and why. We're currently controlling the servos by just making a Java system command doing echo 0 is 150 to dev servo blaster, which isn't really nice. It's pragmatic, I would argue.
It works.
Yeah, it's fast enough also. We would like to take a spin with some AI-based approach to let the car drive itself. For example, take a neural net and train it by driving the car ourselves. But my guess is that we would need to have a lot of training time to train the model. And then we would end up spending, weeks of driving the car around the office, which should be fun, but I don't know. And currently, most of the stuff we have is running on our laptop. So we have the Pi, which is only running the heartbeat control and the core control features, and all the rest is running on a laptop. And it would be, I think, a lot cooler if we would run everything on the Pi. And then we wouldn't have trouble from the network latency pulling the stream over. The question is, will OpenValue run fast enough on the Pi? So that's what we're about to find out. We have the next race, I think, in March. So maybe we have some more success or disaster stories to share next year. We have a couple of minutes left for questions, if you would like to ask questions.
Oh, there's a question over there.
Yes?
Well, you might not know this, but for self-driving cars, how do they handle detours? Like when I drive, there's sometimes detours that pop up.
Yeah.
It's pretty difficult. There's a little sign that says go here or go there.
Right, so the question is, what do these self-driving cars do when there are detours, right? So as a human, you see the signs and then you can decide, well, then I drive just this way and I'll avoid it. Well, I don't know exactly, but it is the case that for example, the Waymo cars only drive in controlled environments. So these environments are constantly being mapped. So my guess is that they will also register those types of things and actually put some sort of blockades or something on its mental map in order for it to avoid it. But you cannot. Well, I think you cannot prepare for everything, right? So I think there was one case in which there was actually some road work somewhere, and the car had to actually move into the other lane, and it didn't get the right of way from a bus, I think, and they hit each other. So unexpected situations will always happen, and that's what makes this so hard. And that's also, of course, why Tesla says you always have to keep your hands on the wheel, just to be able to intervene in those situations
And to cover their asses.
Yeah, and to cover their asses. Yeah, right.
Yeah. Any more questions? Yes.
Question about the development process. I'm sure that your initial process, like first builds all this Java code, then you need to deploy, then to test, regression test, like to make sure that you broke nothing. And after that, I'm sure that it's different. The current process is different from what you have initially, your first attempt. So my question is about those changes in your development process, what you found, what is better when you work with something like with hardware, not software as a typical work.
Yeah, I can answer that. The question is about our development process. So, how do we work with running stuff on the Pi and on a local machine?
I think it all starts with beer-driven development here.
Definitely,
right?
I would say we're currently fairly lean and not adhering to any modern development principles. So we don't have that much tests, since most tests we need to do in a live environment to see how everything reacts.
We do have some approaches that do work.
Yeah, by recording stuff.
Right, so we record the races that it does, and we can actually do the whole computer vision analysis stuff, not only on the live webcam feed, but also on those videos. So that way we can get feedback on our thresholds.
And in terms of development speed, what we typically do is when we develop, we try to run as little as possible on the Pi, because that takes a while to copy there and to deploy, and then run as much as we can on the laptop. We can just restart the Java process there. So we are, I think, this combination of running the least amount of software we can on the Pi, the rest on the laptop, and then finding some ways where we can build and test stuff without running the car. So by recording videos and stuff.
I think one of the things that works really well for us is that because we only use the visual aspect is, for example, with the lane detection algorithms, we just started with a still image, right? No video, just one image or a couple of still images, and then tweak the algorithms to see if it works on detecting the road in those still images, and then we go to video feeds, and then, so that works step by step.
Final question. Yes?
What are your thoughts about weaponizing this platform?
What are our thoughts of weaponizing this platform? Yes, we have thoughts about all sorts of things, but not about weaponizing. I would say it is a cheap way of getting something in some space. So definitely, we don't have any thoughts, obviously. Sorry?
To win the race.
Oh, to win the race. That's a great question, actually. Well, actually, our competitor might be in the room, so we can't disclose any of this. But if you have any ideas, feel free to join us afterwards.
We heard rumors about one of the teams wanting to put a red LED on the back of their car.
For the stopping, that's a great idea.
Right?
Yeah. Okay, to wrap it up, everything we build is on GitHub. GitHub.com/rcdukes. You can see all the code there. There's even a README with, 5 lines of text in there.
Which might help you a bit.
We'll publish the slides online through our Twitter accounts. If you have any questions, feel free to reach out over Twitter. Twitter handles are below on the screen. I really hope you enjoyed your time, and I have one more question. Please take the time to rate this session. I hope you all enjoyed it lots and you give it 5 stars. If you didn't like it that much, please come to us and tell it. So please rate the session. Thanks a lot for your time. Enjoy the conference, and we'll be around for the rest of the day to chat with you.